So in the last part of 5.5c, we are going to talk about using the fundamental theorem of algebra. Now, when something is called the fundamental theorem of anything, you know it's super important. So this is really where everything we've been doing so far is going to come together. And it says, if the degree is positive and greater than 0, then we can break down f of x into that many linear factors. So if our lead term power is x to the 4th, so if it's a 4, there will be 4 of these. If it's a 7, there will be 7 of those, okay? If a factor is complex, so we've come across some where we've had those i's, because that shows up in that plus or minus square root, what we know then is they always come in pairs. So if a 0 is a plus I, then another 0 is a minus I. So they come in pairs. That's super important. So if a plus bi is a factor, then a minus bi is a factor. So an example of that, if we have x plus the square root of 5, we have x minus the square root of 5. Those are conjugates. If we have x plus 3i, we will have x minus 3i. So square roots come in pairs, complex numbers come in pairs. Nothing else is guaranteed to come in pairs, but those things will always come in pairs. So here it says find the zeros of the polynomial, and it happens to have complex zeros. So let's go ahead and take a look. Now, if we do our P over Q list, that would be plus or minus 3, plus or minus 1, and plus or minus 1/3. Those are the only possibilities of zeros that work out nicely. Okay, that's the only possibilities of zeros that work out nicely. Now, you can always factor a polynomial if you know how to factor it. This is one where grouping is a possibility. So we could factor it if you recognize that it is factorable. If you don't know how to factor, if you're not good at factoring, then use your P over Qs. So if you put in 1, you get 16. If you put in -1, you get 8. So not zeros. But if you plug in -3, you do indeed get a 0. Okay? So you can then pull out the associated factor x plus 3. And because it is so nice like that, we can just use synthetic division. So I'm going to pretend like I did not know how to factor it. I'm going to show you what's going to happen. Okay, so we're going to multiply, write it down, add them up. Multiply, write it down, add them up. Multiply, write it down, add them up. It was a factor, so that better be your remainder of 0. Put your x's back on. This was an x cubed, so this is an x squared. We have just factored it to be x plus 3 and 3x squared plus 1, which is exactly what we got just by using grouping. But there we go. Okay. Now, this is not factorable in the sense that we know it, okay? But I'm going to show you how we can break it down, okay? If we do 3x squared plus 1 equals 0. Now, it's not factorable, but it is solvable. 3x squared equals -1, x squared equals -1/3, x equals plus or minus the square root of 1 over the square root of 3. Oh, I'm sorry. Guess what I forgot? See this negative here? It would be here, which we would need to have an I. I'm so sorry. There's an I there. Okay. So the question asks us for the zeros. So the zeros are -3 and plus or minus square root of 3 over 3i. So, and there's lots of ways to do that, but you'll notice if you have one I, because of that plus or minus symbol, you actually will get a pair of i's. So, if they want the linear factorization, we want to set up the polynomial. We don't want to forget the conjugates. It's always some factor a, which sometimes they'll care about and sometimes they won't. It's always x minus the 0 times x minus the 0 times x minus the 0. You can multiply it out except for the a. We can use a point on the graph to find a if they didn't give it to you. And then you can simplify it fully. I am usually just concerned about my a value being 1. But I'll show you what I mean in the next slide. So it says, write a quadratic equation whose roots are -4 and 1. Remember, roots are just a fancy way of saying zeros. Roots are just a fancy way of saying zeros. So our quadratic would be x minus a -4, which would make it a +4, and x minus a 1. And it says the lead coefficient is 4, so just put a 4 out there. Now, that is the quadratic equation that has roots at -4 and +1 and a lead coefficient of 4. That's your a value. If Alex doesn't like that and they want it in an, like polynomial form, you may have to multiply it out. Just FOIL it, hold that 4, multiply the x, multiply the 4, and then multiply everything that you get by 4. Now, let's remind you how i's work for number 12. Remember, I is the square root of -1. So if you get -1 under a radical, don't forget your I, like I almost did on that last problem. And also remember that I squared equals -1. So when we multiply those conjugates out, these are conjugates, one's a positive 6i and one's a negative. Watch what happens. X times x is x squared. X times 6i is 6xi. Negative 6i times x is negative 6xi. And then negative 6xi. Let me say that again. Then negative 6i and positive 6i give me initially a negative 36i squared. Now, it says simplify your answer as much as possible. Because we're simplifying our answer as much as possible, some things that are really nice are going to happen. Those are going to cancel. Remember, I squared is equivalent to -1, so that's really negative 36 times -1, or x squared plus 36. So it should end up simplifying way, way down for you, okay? Now let's take a look at question 13. It says, find a polynomial of degree 4 with real coefficients and the following zeros. Now, they said that this one has a multiplicity of 2, so we'll take care of that. Here I see an I, so I always add on to the list the conjugate. So the conjugate of 1 minus 2i is 1 plus 2i. And then what I'm going to do is I am going to make my polynomial. This factor, or 0 here, gives me a factor of x minus 1, but there's 2 of them. Now you can write x minus 1 squared, or you can write x minus 1 times x minus 1. That doesn't matter to me. And then here, I have to subtract both of those things from x. Remember, it's always x minus all the parts of my 0. So it's going to be x minus 1 plus 2i See, this one switched. We're subtracting, so it became a -1. This one switched. It became a positive. Do it again. So it's going to be x plus 1. No, I'm sorry. This is going to become a -1. So it's going to be x minus 1 minus 2i. Now, if they want it in polynomial form, they want you to multiply it all out. So if that's the case, what I'm going to do is I'm going to combine those two together and combine those two together, because conjugates always work out nicer when they're mushed together. So let's multiply this first piece out. Now that's easy to do. That's just x squared minus 2x plus 1. Like if you were to FOIL, just x times -1, -1 times x, -1 times -1. But the one that's a little harder is this back one. So let's go ahead and do it and just do it step by step. So we're going to get x squared minus x minus 2xi. Now all I did was take this one 3 times. Now I'm going to take the -1 3 times. I'm going to get negative x plus 1 plus 2i. Now I'm going to take the 2i 3 times. I get negative 2xi I'm sorry, it's acting weird. And then I'm going to take 2i times -1. And then 2i times -2i is -4i squared. Now, that piece will usually have lots of things that can either combine or can cancel out. I'm just going to go down my list one more time. Negative, positive. Just go down the list, see what I got. Oh, this one right here. That is a positive 2xi, a negative 2i, and a negative. Okay, so now everything's good. So I have distributed the x 3 times, -1 3 times, 2i 3 times. Okay, so you'll notice that list has 9 things on it. And then look what happens. We have a negative 2xi and a positive 2xi. Cancel. Positive 2i, negative 2i. Cancel. Now this back one doesn't cancel, but remember that's really just a -1 times -4 is +4. And so when I combine everything that's left, I have x squared minus 2x plus 5. And then hopefully from here you could FOIL it out one more time. Use the x squared 3 times, use the -2x 3 times, use the +1 3 times. Okay, so that's that. Now let's do the last example. It's going to be our longest one, question 14. Now question 14 says, for the polynomial below, 1 is a 0 of multiplicity 2. So it says express f of x as a product of linear factors. So this is what we know. We know that x minus 1 goes into it twice. So that means we're going to take it out twice. So I'm going to use synthetic division first. So I'm just going to set up my synthetic division box. So my synthetic division box is ready. So I'm going to multiply, write it down, add them up, multiply, write it down, add them up, multiply, write it down, add them up, multiply. Now you better get a 0 remainder, and we do. So now we have x cubed plus 3x squared plus 25x minus 29. And we are going to do it again because it said that the multiplicity was 2. So there's 2 of them hiding in there. If we looked at the graph, it would bounce at 1. So let's do it again. Now I'm going to use these new coefficients, 1, 3, 25, and negative 29. I'm going to set it up again. So I'm going to multiply, write it down, add them up, multiply, write it down, add them up, multiply, write it down, add them up. I should get a 0 again. So what do we know? So far we know that that was x minus 1 and x minus 1, and guess what? It's also going to be times x squared plus 4x plus 29. Now, there is no way for x squared plus 4x plus 29 to factor, but see what it says here? Express it as a product of linear factorizations. This here is called an irreducible quadratic. This can only be broken down into linear factors if you use the quadratic formula. So we're going to have to use negative b plus or minus the square root minus b squared minus 4ac all over 2a, okay? So I'm going to do that over here to the side. I'm going to factor, or do the quadratic formula for x squared plus 4x plus 29, okay? So when we do that, we get negative b plus or minus the square root of b squared minus 4 times a times c, and 4 times 1 times 29 is a subtraction of 116 over 2a's. So that's negative 4 plus or minus the square root of a negative 100 over 2. Now what's great is 100 is a perfect square. The square root of that is 10. The square root of a negative is I, so that's just negative 4 plus or minus 10i, all divided by 2. Now, the only way you can get rid of this 2 is if you divide all the pieces by 2, okay? So luckily for us, all the pieces are divisible by 2. So we get negative 2 plus or minus 5i. So what do we know? Well, the zeros are 1 and 1, because it happened twice, negative 2 plus 5i, and negative 2 minus 5i. So we can always create the linear factorization by using the zeros. So just because I don't have a lot of room, I'm going to write that as x minus 1 squared, because there's 2 of them. That's the multiplicity. There's a bounce there. And then the other one I'm going to write as x minus each of these. Now to minus 2 terms, just change both sides. So it's going to be plus 2 minus 5i for the first one. It's going to become plus 2 and plus 5i for the second one. And a good check, these should be different. Just the back pieces should be different, and that's the way you found the conjugate. So that is what you would enter into ALEKS. Okay, that's what you would enter into ALEKS. That is the linear factorization. So now you are ready to work on your homework. Okay, so for 56 through 60, it says list all the possibles. You're not finding them. Just list all the possibles. That's just P over Q. 40 through 45, you want to find all solutions. So the real ones and the ones with I's in them. So, that's the one where you would do plus or, plus 1, negative 1. Try to find all the factors. And then 66 and 67, we're only going to do 66. And here, let's cross out 42 and 44. So you have those 4 to do, and 66. And since you're just listing P's and Q's, you can do all of those ones. So that is your 5.5C homework. There you go. Have a good one.